adding local gauge invariant counter terms if you're doing gauge invariant physics. But as we've seen, the Chern's K multiplies something that is gauge invariant, but not built out of integrating a local gauge invariant density. And so it doesn't get renormalized. Okay? So, this is a very interesting thing about the Chern Simons coupling. It does not get renormalized and it does not flow. Contrast this with the Yang-Mills coupling in, let's say, a 4-dimensional field theory. Yang-Mills coupling in 3-dimensional theories are dimension full, so in a Wilsonian sense always flow. But in 4-dimensional theory, it's less trivial. Dimensionally they dimensionless, so you might have thought there was a chance they wouldn't flow, but as we know from decades of experience, that expectation is false in general. Yang-Mills couplings almost always flow unless there's a very special reason for them not to. That very special reason is usually supersymmetry. Okay? So this means that it's very hard to make conformal field theories involving gauge fields in 4 dimensions. Just because the theory might be conformal when you write it down classically, you start doing quantum mechanics with it, unless you've done some very special tuning, usually supersymmetry. The theory starts to flow. It's no longer conformal, like in QCD. Okay, certainly it's very hard to make 1-parameter lines of conformal field theories. Maybe sometimes special points, but certainly very hard to make lines. Okay, now that's a bit of an unfortunate circumstance. Why is it unfortunate? It's unfortunate because as we've learned to appreciate more and more since 1997, or earlier than that as well, over the last 20 years, when you've got a 1-parameter line of conformal field theories, one end of which is weakly coupled, there's often an interesting question. What happens at the extreme other end? And that interesting question sometimes has interesting answers. In the case of N equals 4 Yang-Mills, that interesting question had an interesting answer. That answer was gravity. In the case of N equals 4 Yang-Mills, where the coupling is G rather than lambda at fixed N, that interesting question had a slightly less interesting answer. That was self-duality. Okay? And this kind of thing happens in supersymmetric quantum field theories all around the place. So when you've got 1-parameter lines, where you can control the theory at one end because it's perturbative, there's often an interesting question. What happens at the other end? Okay? But as we've just seen in 4-dimensional field theories, gauge theories, usually you can't even try to make wild conjectures about what might be happening in the absence of supersymmetry, because usually there isn't even a question in the absence of supersymmetry. You don't have these lines. Okay? So the questions are by themselves sort of inherently supersymmetric, which is a bit disappointing for various reasons. We won't get it. Okay? This is not the case in 3 dimensions. This is not the case because the Chern Simons coupling does not run for a reason that has absolutely nothing to do with supersymmetry. Okay? Supersymmetric integers are as good as non-supersymmetric integers. Okay? They can't run. Okay. Now, what this means is that it's very easy to make effective large N fixed lines of conformal field theories in 3 dimensions that have nothing to do with supersymmetry. You know, not to get it wrong, I like supersymmetric theories, okay? But it's interesting to see what phenomena of quantum field theories are a consequence of supersymmetry and what phenomena extend beyond it. It's an interesting question that often we cannot answer. Okay, so if you have an opportunity to answer this question, you should try to answer it. Okay, so let me give you an example of a quantum field theory that's without of a effective fixed line, a bunch of fixed points, which will effectively be a fixed line of theories that is conformally embedded. Yeah, the example is very simple. Consider psi bar d slash psi plus Chern Simons. Okay, a fermion in any representation of the H group, minimally coupled to Chern Simons theory. Okay, I'm claiming that this theory, at least in a finite neighborhood about k equals infinity, at least in a finite neighborhood about weak coupling, is a defines, for every value of k, defines a conformal field theory. Why is that? The argument is one line. Okay? You see, what are the operators that could possibly run in this theory? What are a set of marginal and relevant operators? Well, there's the mass term for the fermion, but we can fine-tune that away or work in dimensional regularization, so it'll never be generated. Okay, good. Well, you might say, well, there's a kinetic term for the gauge boson. But as we've just argued, that cannot run. Okay? So, every other operator you can write down in the theory is irrelevant, so will not be generated. End of story. Okay? Therefore, the theory is conformally invariant. Isn't that a simple proof? I mean, it's really that simple. Okay? So, this, for every value of k, and every value of the gauge group gives you a conformal field theory. Now, k and n are isolated points. But we can make this an effective fixed line by working in the 't Hooft large n limit. N goes to infinity. K goes to infinity. N by k, which is equal to lambda, is equal to fixed. See, in this limit, the fact that n and k are integers is basically irrelevant because they're such large integers. So lambda is an effectively continuous number, and physics of these large N Chern Simons theories are parameterized by an effective fixed line, which is lambda. Lambda, as you all know, is the 't Hooft coupling of these Chern Simons theories. It's the thing that weights two loop graphs compared to one loop graphs. Tells you how strongly coupled your theory is. Okay, so at 0 lambda, our theory is perturbative. At very strong lambda, it's very strongly coupled. Okay, so for this theory, there's an interesting question in any representation of the gauge group. Okay, what happens to this theory at large lambda? It's a really nice question, and in general, I don't know the answer. I think nobody knows the answer. It's very interesting because we'll see more concretely examples of supersymmetric theories where the answer can be very, very interesting. Okay, but this was a question for just a non-supersymmetric. Okay, now I'm going to do 5 or 10 minutes of review of some supersymmetric phenomenology for a particular supersymmetric theory. The one that you all know and love the best, the N equals 6 theory. Which we will understand how the physics of this theory behaves as a function of this lambda, and see how very interesting things can happen. That will motivate us to set up the questions in a non-supersymmetric context. Okay, so I'm going to look at ABJ theory. ABJ theory, as you all know, I won't really review it, I just remind you, is a theory, a UN times UM theory at level k and minus k, with 2 bifundamental and 2 anti-bifundamental chiral multiplets, and it's N equals 6 supersymmetric. Details don't matter. Okay, the point is that everything we've said here applies to ABJ theory. Okay, we'll study them, ABJ theory in the limit, n goes to infinity, k goes to infinity, m goes to infinity, with 2 ratios held fixed. Let's say n by k is equal to lambda, and m by n is equal to x. Okay? So we've got a 2-dimension effectively continuous moduli space for these theories. And I want to remind you what we know of the behavior of this theory on this moduli space. So let's draw that. Oops, we'll maybe draw it there. Let's draw a diagram. On this axis I've drawn x, and on this axis I've drawn lambda. Now, I will choose x to be less than equal to 1, by which I mean I will choose n to be the larger of the 2 gauge groups. I lose no generality in doing that. Okay? So my diagram ends at x equals 1. This is a line that's supposed to be vertical. Okay. Now, some of you may know that ABJ theory is believed not to have at least a supersymmetric, possibly no, possibly not a stable vacuum, unless K is greater than or equal to mod n by n. Sorry, n by m. Okay, so we'll restrict our study to this region because the theory certainly does not have a supersymmetric vacuum. When this is violated, it's plausible that it has no vacuum. Okay, so since n is greater than m, we can remove the mod. What is this condition? This condition, let's divide through by n. Let's divide through by n. Okay, so this is 1 by lambda, if I divide through by n, is greater than or equal to 1 minus x. So lambda is less than or equal to 1 over 1 minus x. Okay, so or lambda into 1 minus x is less than or equal to 1. So when x is equal to 0, lambda has to be less than 1. When x is equal to 1, lambda has to be less than infinity, and this curve goes here. So the moduli space is the region to the bottom of this curve. Okay? Now, something else that will play an important role through my lectures, because we'll find a non-supersymmetric version of this duality, is that this ABJ theory enjoys invariance under a version of what is sometimes referred to as Givion-Kutuzov duality. Okay? And the statement of the duality is as follows. ABJ theory is self-dual. Okay? Under the map, the theory with n, k, and m, up to signs, which I won't keep track of, okay? I'm dealing with modulus values, goes to the theory with k minus n plus 2m. K and m. The theory with parameters nkm and k minus m plus 2m km are the same theories. The theory enjoys a self-duality under this Seiberg-like flip of parameters. Okay, I'm not going to, at this point, review how we know this or why we know it's true. We'll get some flavor for it from a quite a unique point of view as we go through our lecture. Okay, so now I'm just going to assume that this is true and see what this says for this moduli space. Okay, so what does this flip do to lambda and x? Okay, so what is the new value of x? So x prime is equal to m prime by n prime, but m prime is the same as m, and n prime is k minus n plus 2m. Dividing through by n, this is x, divided by 1 by lambda minus 1 minus 2x. Okay, so I'll write that here. X prime is equal to lambda x over 1 minus lambda into 1 minus 2x. That was x prime. What about lambda prime? Lambda prime is equal to this quantity, k minus n plus 2m over k, which is equal to 1 minus lambda plus into 1 minus 2x. Okay, so in terms of x and lambda, this is what this Givion-Kutuzov duality does. Now notice that in particular, x prime lambda prime is equal to x lambda, as you see immediately by just multiplying the right hand sides of these relations. Okay? So, notice also that if you're at this edge here, if lambda obeys this value, you can easily check that maps you to another point at x equals 1. It's 1 minute of algebra with these formulas. Okay? So the lines lambda x equals 1 are somewhat like this. I'm sorry, lambda x equals constant are somewhat like this. Okay? A small constant gives you something that hugs the axes. Larger constants give you things that do this. And very large constants go up to infinity. Okay? So, what duality does is relate the physics of a theory on this line here to this point, here to this point, here to this point, and so on. So it closes off this moduli space. Okay? In particular, at near x equals 0, what duality does is just take lambda prime is 1 minus lambda. Okay? So it gives you a map between theories near lambda equals 1 and the theories near lambda equals 0. In the larger moduli space, it's something more complicated. Okay? Now, in this full moduli space, we've got quite a lot of interesting things happening. Firstly, we've got this interesting duality that relates basically a priori unrelated pairs of theories on this moduli space. And secondly, we've got this clearly special region up there. Okay? That happens only at x equals 1. And that's the place where we get supergravity. Lambda goes to infinity, x is 1, we get supergravity. Okay? So this moduli space of ABJ theory is very interesting. There's a naive moduli space, it's got relations under duality, and it's got this cone funnel region, the edge of which is supergravity. Okay? So this theory is clearly a very interesting theory, exhibiting clearly very interesting dynamics. Okay? This is an existence proof that matter Chern Simons theories can display very interesting dynamics. That's the reason I introduced this thing. Do you? Yes.
So there is no marginal deformation that allows you to move on this one.
No.
So is there a sense in which in the large enemy you can still define some notion of metric on this one space?
Good. I'm not right. It's not clear there's anything to compute the 2-point function of, as you're saying. That's an interesting question. I don't know the answer. Okay. So, fine. Now we're going to leave the ABJ theory behind. This is just presented as one example of a theory where there's something quite interesting, a large moduli space, interesting things happening. Okay, we're motivated by this fact to study non-supersymmetric moduli spaces, which, as I emphasized, exist. Okay, in a way that they need not in 4 dimensions. Okay, so I think that's it for my motivational introduction. I will now start, unless there are questions or comments or some discussion, I will start actually turning to the theories we will actually study in these lectures and start posing the questions we will actually tackle. Okay, but any questions or comments before we do that?
It sounds like from the supergravity point of view, there might be a notion of metric, since in that case, you can make this parents can use just forgetting about fluxionalization condition. So maybe one can calculate something from supergravity.
Right. But okay, so right. It's the string coupling, in some sense, that is, yeah. It could well be. Yeah. Right. So that's a good argument. But there should be some effective field theory notion as well, I think. Yeah. Okay, but I don't know how to characterize that. That's an interesting question. Please go ahead.
Do you need to worry about the parity anomaly?
Well, parity is not a symmetry of these theories, but a parity gauge anomaly, is that what you're talking about?
When you have massive subfermions, then the renormalization might introduce a mass scale.
Might introduce a mass scale. Yeah. Let's see. So, in general, when n is not equal to m, the theory is not parity invariant. Okay? Now,
no, it does not introduce a mass scale. If you have a massive fermion, the renormalization is going to shift k by
that's
the proportional sign of the mass, but if the mass is 0, that's a renormalization scheme dependent statement, and you can always, even if that were present, you can choose the definition in your Baird level k so that
absorb it away.
Yeah.
Right. Yeah. Right. I don't think this. Right. Exactly. Okay. Excellent. Any other questions or comments? Okay. motivated by all of these disparate ideas, what we're going to try to do in these lectures is study, to the extent that we can, the moduli space of a simple set of non-supersymmetric relativistic matter-Chern Simons series. Okay? Right. Let's study a simple set of relativistic matter-Chern Simons theories. And now I'm going to introduce the theories to you. Okay. The first theory I will study, okay, as we go on, we will enlarge the list of theories we study. Okay. But to start with, the first theory we'll study is one that I've already introduced. Its action is psi bar d slash psi plus k by 4 pi times ADA plus 2 pi 3 cube, where I specify that psi is in the fundamental representation of the gauge group. When I last introduced this theory, psi was in any representation of the gauge group. That was sufficient to show conformal invariance of this theory. But now I'm restricting to a particular representation of the gauge group, the fundamental representation. And let me give you the reason why I'm doing this. Why is the fundamental representation a particularly interesting representation of the gauge group in this context? The reason is that I am going to be studying these theories in the large n limit. This kind of large n limit. N goes to infinity, k goes to infinity, n by k held fixed. Why am I studying these theories in large n limit? Well, because I need a technical tool to allow me to do calculations. Now, why am I studying fundamental theories? This is interesting. You see, large n limits simplify physics, but as all of you know, not very dramatically for theories with matrix degrees of freedom. Nobody's managed to solve QCD in the large n limit. It's not for want of trying. It's a very complicated theory. Matrices give you very complicated large n limits. Simpler than the finite n theory, but not that much simpler. Okay? On the other hand, if anyone has looked at Coleman's book, Aspects of Symmetry, knows that theories with fundamental matter in the large n limit are very easy to solve. So, that's the reason I'm going to study the theory with fundamental matter. Now, some of you are saying, well, QCD has fundamental quarks. That didn't mean that QCD with fundamental quarks was easy to solve with the large n limit. It wasn't the quarks that were the problem. It was the QCD. Right? So, what difference, what representation you put your matter? But remember, QCD was dealing with real stuff. Chern Simons theory is smoke and mirrors. Okay? Equation of motion F equals 0. There's nothing there. Okay? So, what we're dealing with is matrices, but it's smoke and mirrors. And then real stuff, but that's fundamental. So, in the large n limit, it is plausible that we can take these theories and solve them, perhaps not as easily as Coleman manages to solve the ON vector model, but maybe almost as easily. That's the hope. Okay? So, just to say this again, there seems like there is a window of opportunity in understanding exact results, exact strong coupling results, okay? All coupling results in these theories. Okay? It's a very small window. That window forces us to 3 dimensions. Because in every other dimension there are physical degrees of freedom with the gauge boson as far as I know. In a sensible gauge boson coupling theory. And it forces us to fundamental matter. Okay? But that's a small but non-trivial window of opportunity. Should be exploited because with this window of opportunity we'll be able to do exact calculations at all values of the coupling for these matter-Chern Simons theories without supersymmetry and see what we can discover. That is the game we're going to play. Is the philosophy clear? Excellent. So this is one theory I will study. The second theory I will study is the bosonic analog of this theory. Okay? The bosonic analog of this theory is the following. Okay, and let's call this K fermion. This is K boson. Okay, and I'll actually study this fermion theory also with the fermion mass. Okay, just because I can. MF psi bar psi. Okay. Now, the fermionic theory, at least at zero mass, was conformally invariant. This bosonic theory clearly is not, because it's got a dimensional coupling constant, namely this B form. Okay? But there is a particular simple scaling limit of this theory that gives conformally invariant physics. And I want to explain that to you. Something many of you know, but it's elementary, but let me just tell you anyway. Okay. See, suppose I take this theory and I plus B4 by 2 phi bar phi the whole thing squared. And I add a Lagrange multiplier to this theory in a way that doesn't change the theory. A way to do that is to add sigma n by 2 b4 sigma minus b4 phi bar phi by n plus m squared phi bar phi the whole thing squared plus the Chern Simons which are not right here. Okay. Now, why have I done this addition? I've done this addition so that two things will happen. You see, firstly, what have I done? I've added a new field, but in a way that its equation of motion will set the new term that I've added to the Lagrangian to 0. So I've not changed it here. Okay? Obviously, the equation of motion will set sigma equal to this, not change the theory at all. But if I just expand out now what I've added, I've done it in a way so that the b4 by 2, did I want the 2? No 2. The b4 phi bar phi square term cancels because sorry, this term, sorry, and I wanted an n here, I need an n here, sorry about that. Yes. I want to have this in a way so I can take the large n limit. This was order n squared, so I need a 1 by n explicitly. Yeah, right, so now I think this is correct. The b4 by phi bar phi, the whole thing squared, oof, and I've got a sign now. Minus, now I need minus. Maybe now we'll finally go. Okay. The b4 phi bar phi by n, the whole thing squared, coupled with n by 2 b4, will cancel this term. And if I've got all my signs right, the cross term between phi bar phi and m, sorry, the cross term between phi bar phi and m squared, okay, will cancel this term here. Okay, so just by rewriting this theory, you'll excuse me if I've got one to signs wrong here. D phi bar, d phi. This and these have cancelled, but what remains is this term which is plus sigma phi bar phi and a term that is plus n m squared by 2b4 times sigma plus a term that's just cosmological constant, something that involves no fields. The term that I get by squaring this m squared, which I'll ignore. Fine. Okay. Now,